All right, number 5 asks us to write the dimension of each matrix here. Dimension being number of rows by number of columns. So this is 2 rows by 2 columns. This one has 1 row and 4 columns, so it's a 1 by 4. 3 rows by 2 columns, and 3 rows by 4 columns. Then we want to find the product of 2 of these, for which the product is defined. And I think the only one that's going to work is if I multiply C by A, because I get a 3 by 2 times a 2 by 2, and you have to have that inner dimension being the same, and then we know what we're going to get is a 3 by 2 out of that. So here's C, 1, 2, 3, 4, 5, 6, and here's A, 1, 2, 2, 4. And so I go across the rows and down the columns. So 1 times 1, 2 times 2, that's 5. 1 times 2 is 2, 2 times 4 is 8, that's 10. Add those together. Then I go to the next row, 3 plus 8 is 11. 6 plus 16 is 22. 5, and so now I go down to the bottom row. 5 times plus 12 is 17. And 10 plus 24 is 34. So assuming I did all my arithmetic correctly, there's your product matrix. Okay, on this one, we're asked to show that these vectors are linearly independent. And so what I do is I put them in a matrix and then take their determinant. And that's what we're told to do, using determinant to do this. So there's my matrix. I've got it in determinant form. And you can make this a little simpler, possibly by doing a little Gaussian elimination, but there's a bunch of 1s and 0s, so it's probably easy enough to just go ahead and do it. I'm going to go across this top row. I get 1, eliminating the top row in the first column. The leftover determinant is -1, -1, 0, 1. And then minus, next I'm going to do -1, and covering up the middle column in the first row, here's what's left, 1, 1, -1, 1. So I get 1 times, this is just going to be -1 plus 0, so it's 1 times -1. And then I've got minus a -1, so I'm just going to go ahead and say plus 1. And then here I get a 1 minus a -1, so that's 2. So that's going to equal 1, which is not 0. And that means if the determinant's not 0, then it is. Those vectors are linearly independent. And now I want to express T as a linear combination of u, v, and w. So I'd like to find C1 plus C2 plus C3 times each of those vectors such that I get T when I take that combination. So that gives me the following matrix, the same as this determinant matrix, where those vectors are the columns, augmented by the T matrix, this T vector. And the unknowns here are the C1, C2, and C3, so I'm going to solve, and then when I work that out, it'll tell me what each of those constants are. So let's see, I'm going to just take minus row 1 and add it to each of those. So let me write it here. Minus row 1 is -1 plus 1, 0, -1. I'm going to add it to each of those other two to get, so minus row 1 plus row 2 is going to be my new row 2, minus row 1 plus row 3 is going to be a new row 3. So the first row is going to stay the same. Second row, I'm going to add, I get 0. 1 and -1, I get another 0. 0 and -1, I get -1. -1 and 2, I get 1. And in the bottom row, I get 0, 1, 1, and 2. I'm done now. I mean, you can switch these two rows if you want, but right here, this equation tells me what C3 is. So from this one, I get that C3, negative C3 is 1, so C3 is -1. And if C3 is -1, from this one, I got C2 plus C3 equal 2, which means C2 minus 1 equal 2, so C2 is going to be 3. And now putting C2 into this top one, I've got C1 minus C2 equals 1, but C2 is 3, so that's going to be C1 minus 3 is 1, so C1 is going to be 4. So I get 4, 3, minus 1. Let's go try that and make sure it works. So I got 4 of these, 3 of these, second one, the V, and I think I said minus 1. Yeah, minus 1 on the last one. So let's hope we get 1, 2, 3. I get 4 minus 3, that's 1. I get 4 minus 3 plus 1, that's 2. And then I get 4 minus 1, that's 3. So it does work.